Welcome to When Music Matters from VAC. I'm Kevin Hayes. Today I thought it would be good to dig into some technical issues, and one of the questions and areas of confusion that I hear quite often, even from people who you'd be surprised to know have this area of question, are the interrelationship between certain terms. Triode versus pentode, single-ended versus push-pull, ultralinear versus non-ultralinear, Class A versus Class AB versus Class B. And I will give you a short synopsis before we go into the first of what is probably going to be a three-part discussion on this. If something is running single-ended, it has to be Class A by definition. But things that are running Class A don't need to be triode or single-ended, or the terms overlap in areas, but they don't mean the same things. So let's begin with tube types, triodes, pentodes, and so forth. Somewhat technical, going to try to make it as easy as possible. Start with a basic light bulb. You've got a hot glowing filament inside of an evacuated glass in a vacuum. Edison discovered back in the 1800s that that filament would boil off a cloud of electrons, negatively charged particles, that would form a cloud around that hot device. If you then put another metal object in the vacuum with that, and you provide a positive charge to that item, the electrons will be drawn to it. Electrons are negative. They're attracted to opposites. They're attracted to a positive charge. So he discovered electron flow in that direction. But if you charge that plate negatively, no electrons flow to it. Negative repels negative. That is a diode. It allows electron current flow in one direction only, but not the other. It's sort of like a check valve. It's a one-way device. And it was initially called a rectifier because it's commonly used to take AC waveforms and turn them into choppy DC waveforms, which are then filtered by other power supply elements. So it was named the diode only years later, in the early 1900s, after Lee DeForest inserted a control grid between the filament, the electron source, and the metal object that drew the electrons off, which we call the anode or the plate. That third element in the tube was coined as a triode tube. So you have the filament, the control grid, and the plate or anode. Now, the neat thing about the triode is, as you impose charges on the control grid, they can completely aid or interrupt the flow of electrons from the filament to the plate without requiring any power on that control grid. And so it's like someone now put a control valve in the flow of the electrons. One of the reasons why we sometimes call a tube an electron valve. And the three elements were from the Greek triode, three in the path. At that point they said, oh, let's call the two-element one a diode, di being two and ode being the path of flow. So as years go by, the vacuum inside the bulb is improved. The earliest vacuum tubes were really more like low atmosphere tubes as opposed to vacuum tubes. But we learned over the years how to draw stronger, deeper vacuums and to burn up the impurities inside the bottle as part of the manufacturing process. And then tube engineers going forward found ways to improve the efficiency or certain aspects of the performance of the tube. The first step was putting a second grid called a screen grid in the tube, which formed something called a tetrode. Tetrodes are very useful in many applications, but not in their original form very useful for audio. They don't have good linearity, and they have very high output impedance. A few years later, I think it was the engineers at Philips, inserted a third grid in the tube, creating a pentode, 5 elements, pent, called the suppressor grid, and that got the pentode to begin working very nicely. And around that same time, engineers at the British GE company and their correspondents at RCA in the US developed a form of tetrode called a beam power tube, which only has 4 elements really, but performs like it's the 5-element tube. And that beam power tube has become pretty ubiquitous in audio over the years. You'll recognize tube types as the 6L6GC or the 6V6 from guitar amplifiers, the KT66s, 77s, KT88s from higher power amplifiers and high quality audio amplifiers. So a few things to note and one additional development to note. That original diode and triode I described to you used simply a hot filament like a vacuum, like a light bulb filament. Later on, they discovered a way to put a sleeve around that contained emittive coatings that emitted electrons even better, and the filament then became simply a heater, and the actual emitting element of the tube was the cathode wrapped around the heater. We don't call that an extra element because the cathode electrically replaces the filament in terms of the emitting control grid anode circuit. So most modern electron tubes have an indirectly heated cathode and a control grid and an anode, and may also then have either a suppressor grid and a beam forming element or two more grids. Typical example of a 3-grid pentode tube for audio is the EL34, although there have been EL34s made also as beam power tubes, which gets confusing and you really don't need to know that. Few things to think about here. The structure of a vacuum tube is really very pure and very simple in that theoretical sense. You simply have a reservoir of electrons and a place for them to go, and their transit is through as near a vacuum as man can make. So there's not much in there to get in the way of the flow of things and the sort of natural behavior of the elements. Secondly, whenever you put any two metal structures near each other, they form a capacitance, usually referred to in this context as a stray capacitance. In a vacuum tube, let's say you have a stray capacitance between the anode and the cathode, or the screen grid and the anode. The dielectric for that capacitance is a vacuum, which is the best, purest, best behaving dielectric we know of that exists. And secondly, because vacuum has the properties it does, the amount of capacity which can develop between those elements is very, very small. So the stray behaviors of the tube are as perfect as one can envision them being. And that's in very stark contrast to a semiconductor, a transistor, where the dielectric material is that crystal structure from which the transistor is made. It's not particularly well behaved in dielectric terms, and it's much more efficient in a capacitor sense, meaning there's much more stray capacitance amount present in a transistor. And lastly, in many types of transistors, the amount of the capacitance that exists, the stray capacitance, actually varies with signal level. In other words, the stray capacity is modulated by the signal or vice versa, which is hardly an ideal situation. So there's a little bit of the basic introduction to a vacuum tube and how it works and the various types of tubes. And in the upcoming episodes, we'll talk about classes of operation and push-pull versus single-ended. So I hope you'll stay tuned and tune in again for those. And as always, if you have questions you'd like to see addressed here on When Music Matters, write to us at info@vac-amps.com. Thanks and have a great day.